Now we're going to do some practice problems, some harder practice problems with antiderivatives, section 6.2 and 6.3. So first example, let's look at this complicated antiderivative. Since there's no bounds on the integral, this is an indefinite integral, which means we're going to find all antiderivatives of the function, which means we're going to have a plus c at the end. So here we go. We have 3 over x. Actually, this is going to be a few antiderivatives. We're going to have antiderivative of 3 over x plus the antiderivative of 4th root, which is x to the 1/4, plus the antiderivative of pi x minus the antiderivative of 5. So 3 over x, we have this 3 we can bring out in front, and this is going to give us just a 3 natural log of absolute value of x. Remembering the absolute value bars are important. The x to the 1/4 is the reverse power rule, so we are going to increase the power by 1, and we are going to divide by that new exponent 5/4. We have another reverse power rule. We have pi, which is a constant we bring out in front, and we're going to increase the power by 1, and we're going to divide by that new power. And then when I have a constant, I'm just going to slap an x onto it, 5x, and don't forget that we have a plus c at the end. There is our set of all antiderivatives of that complicated function. Next example, we're going to find the area under the graph y equals e to the 5x from 1 to 2. So let's think about what this means. This is going to be e to the 5x looks something like this, exponential function, and we're trying to find the area from 1 to 2 from the function to the x-axis. Now this area is not easy to find just by itself. It's a curvy line. You don't have a nice area formula, but we now know that we can write this as the integral from 1 to 2 of e to the 5x dx. And this is one of our antiderivatives that we have a nice formula for. This is going to be e to the 5x, so we're going to divide by that 5. We're going to evaluate from 1 to 2, which means that we're going to write this as 1/5 e to the 5 times 2 minus 1/5 e to the 5 times 1, using the fundamental theorem of calculus. And maybe we could simplify this being 1/5 e to the 10th minus 1/5 e to the 5. That is a number. It's giving us the area under the curve. So area is a definite integral. We can find a definite integral by finding an antiderivative and then plugging in the bounds. All right, next example is just a definite integral. We have some complicated antiderivatives. So first, let's rewrite this as, I guess it's already rewritten in a nice form, but we're going to find the antiderivative of both of these. X to the -2, we're going to use the reverse power rule. So that's going to be increase the power by 1 and divide by the new power. And for cosine of 2x, we have this sine of 2x, so we're going to divide by that 2. And we're going to evaluate from 1 to 2. That means that we are going to plug in the top bound, and we're going to subtract off plugging in the bottom bound. So the top bound is going to be a -2 to the -1 plus 1/2 sine 2 times 2. And the bottom bound is going to be a -1 to the -1 plus 1/2 sine of 2 times 1. Putting it all together, this is going to be a negative 1/2 plus 1/2 sine of 4 plus 1 minus 1/2 sine of 2. Note that I did some distribution of this negative to both terms, and this is a number, a complicated number that we get out at the end. Think about if there's units here, this would be an area, so this is some units squared. Since we're not given any units in the problem, we don't necessarily need that in our answer. And last example here is about improper integrals. So we're going to kind of dive through this a little bit more than we did in the previous video. Let's consider the improper integral from 1 to infinity of 1 over square root of x dx. Using a computer, it can be found that for the following values of b, we have that this integral 1 to b, 1 over square root of x dx, has different values. So what we're doing here is we have one over square root of x. Just going to look something like this. What we're doing is we are finding the area from 1 to 100 to 1,000. This is not to scale, but that's okay, to 10,000. So here's the area from 1 to 100. We found that this area is 18. Then we did the area from 1 to 1,000, and that area is 61.2. And then we do the area from 1 to 10,000. You see that that area is 198. So we could just keep on going and finding bigger and bigger numbers to plug in for b there. What we're going to do is we want to see what happens if I let b get bigger and bigger. And it seems that as b gets larger, the integral doesn't approach one number. And that's going to be our idea of divergence. We're going to see this specifically with the fundamental theorem of calculus and a limit. So this proper integral that we've been looking at, we can do with the fundamental theorem of calculus. So this is going to be the antiderivative of 1 over square root of x. Let's rewrite this as 1 to be x to the negative 1/2. Antiderivative is going to be increase the power by 1 and divide by the new power. We're going to evaluate at the bounds, and we can rewrite this as 2 x to the 1/2 from 1 to b. Plugging in the bounds, this is going to be 2b to the 1/2 minus 2 times 1 to the 1/2. Or total, this is going to be 2b to the 1/2 minus 2. And this is where those numbers 18, 61, and 198, that comes from plugging into the formula 2b to the 1/2 minus 2. So that's true for any finite value of b, but what happens if we let b get bigger and bigger? Well, that's our idea of a limit from Calc 1, that if I look at the limit as b goes to infinity of this integral, 1 to b x, or 1 over square root of x dx, now we're saying that's the same thing as 2b to the 1/2 minus 2. And this limit is equal to infinity because this guy blows up and gets bigger and bigger and bigger. The minus 2 doesn't make a difference. This gets bigger and bigger, so we're going to say that this diverges, and we could say that it diverges to infinity. There's dealing with improper integrals can be a lot of work. We're going to see this again in chapter 7 when we talk about probability. And we will do some more work on that when we get to that point. If you have questions on this, please make sure that you ask. And at this point, you should be doing the weekly quiz as well as the Wiley Plus homework and the weekly homework.